بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على سيدنا محمد وعلى آله وصحبه أجمعين. I would like to welcome my students from grade 12 into their second and final lesson in chapter 3 and in this year as well. So in chapter 4, I'm sorry, connect sections. So in this lesson we will discuss the remaining shapes of the conic sections, and this is going to be the last lesson for this year. Now, so as we said previously in the first video, that conic sections are actually four shapes. These are the circle, the parabola, the ellipse, and the hyperbola. Now, you might ask yourself, why do we call them conic sections? And why do we only have these shapes? What's the relationship between them? And to show you that, I am going to show you this applet. Now look at this, guys. Now, this is what we mean by conic sections. You have two cones here. You see, we have two cones here. This is the first cone, and there's a second cone attached to it. We call these vertical cones. So we have two vertical cones, and then we have this sheet, and this sheet now is cutting through the cone. So when we cut through the cone, we get a conic section. Now, the conic section that we do, that we get, when the sheet is like this, it's horizontal. So the sheet now is horizontal. So the conic section that we get is actually a complete circle. Now we're looking at the cone from the top. This is a complete circle. So this circle now is the first of the conic sections. That's why the first one of the conic sections is a circle. Okay, now what would happen if we change the angle at which this sheet is cutting the cone? Now let's look at this carefully. So this is the cone now, and the sheet is there, and I'm going to start changing the angle of the sheet. So the sheet is going to start tilting a little bit. Now you might not be able to see it well from this angle, but let's try to change the angle. So here it is. So what shape do we get if we start tilting the angle? Now, if we start tilting the angle, the shape that we're going to get is not a circle, but this shape that we're going to get is an ellipse. So this is the second shape that we get from conic sections, which is the ellipse. This one, and this is going to be discussed today. So this is an ellipse. And how do we get an ellipse? Simply by changing the angle of the section. So when we change the angle of the section, now we get an ellipse, right? If we keep increasing this angle, this ellipse is going to reach to the edge of the cone and then suddenly changes into a parabola. So this shape now we have in front of you is a parabola. This is the shape that we have studied in the previous class. So we get a circle if the sheet is completely horizontal. We get an ellipse once we start tilting the sheet a little bit until we reach to the end of the cone, so we get a parabola. Now, if we keep tilting the sheet even more, it will start cutting the second cone down below, and we will get two curves, and these two curves are what we call the hyperbola. So this is now a hyperbola. A hyperbola is going to be two curves at once, not only one curve, but two curves together. They look like two parabolae, one on top and the other one in the bottom, or to the left and to the right. So these are the four conic sections, and this is how we get them. We get a parabola like this, we get a hyperbola like this, we get an ellipse like this, and we get a circle just by putting the sheet horizontally. Now, the picture that I've shown you here before, this is actually a hyperbola. You see there is a hyperbola. This is the Eiffel Tower in France, in Paris. This is the Eiffel Tower from the bottom. So this is a hyperbola here. This is one of the sides and this is the other side. Or we can say it's this one and this one. It's one of the applications in which we use conic sections. So conic sections, again, are circles, parabolae, and ellipses and hyperbolae. So circles, a circle is the first kind, the parabola is the second kind, the ellipse is the third kind, and the hyperbola is the fourth kind. The objectives in this lesson, we've studied the parabola before, so in this lesson we will pay more attention into the ellipse and the hyperbola, and we will talk about the circle as a special case of the ellipse. Okay, so the objectives of this lesson are the following. By the end of this lesson, you should be able to write the equation of an ellipse in a standard position from a given data. So we will study the equation of the ellipse in the standard position. So ellipse in the standard position. And we will also conclude the data about an ellipse in the standard position using its equation. So from the equation, we will get some data about the ellipse, and we will see what kind of data we can get. And we will do the same thing with the hyperbola. So we will be able to write the equation of the hyperbola from in the standard position as well, from given data. And we will be able to conclude some data from the hyperbola, from the equation of the hyperbola. So these are the four main objectives of this lesson. And now let's move on to definitions. So now let's start with some definitions of these conic sections. And we will start with the definition of the ellipse. So the ellipse is defined as the locus of a moving point. Now we have seen this word before with the parabola. The locus, we said that the locus means the path. So when they say the locus of a moving point, they mean the path taken by a moving point. So the locus is the locus of a moving point whose sum of distances. Now we have a sum here. It means addition of distances. So we don't have one distance. We have more than one distance to two fixed points. Okay, now we have two fixed points. In the parabola, we had only one fixed point, which was called the focus. Now we have two fixed points, and they're called the foci, or sometimes they're called the foci, depends on the accent, or the British or the American accent. So it's the foci or the foci is equal, so the sum of the distances to two fixed points equals to a fixed value that is called 2a. Okay, to understand this definition better, let's look at an ellipse. So this is an ellipse now. We see we have an ellipse here. We have two fixed points. These fixed points are at 3 and 0 and minus 3 and 0. Okay? Now let's check the following relation. Look at this, guys. Look at the distances between this point here, where the circle is, and the first focus, and the distance between this point and the second focus. You notice that there are different distances. This is 2.77, this is 7.23. But if we add them together, 7.23 and 2.77, we will get 10. Okay, if we move this point to another place, I will have different distances, 3.15 and 6.85. But if I add them, I will still get 10. And if I keep moving it anywhere else, so I will always get 10. Look at the answer here of the sum. The sum is always going to be 10. So this is the definition of the ellipse. So the ellipse is the path. This is the path of a moving point. This is a moving point whose sum of distances, the sum of the distances to two fixed points is always a fixed value, and that fixed value is 2a here, which is 10. Of course, it doesn't have to be 10 all the time. If this ellipse is a little bit bigger, you'll see that the sum is different. But again, the sum is always fixed. So the sum is 20 in this case. It is fixed at 20. If you move the focus, the foci to here, to 4 for example, the sum is fixed to 13.33 and so on. So the ellipse is the path of a moving point whose sum of distances to two fixed points, or the foci, equals to a fixed value which is equal to 2a. Now, so this is an ellipse as we have seen in the previous animation, and this is the definition. Now, the second the second conic section that we will take an interest in this class is the hyperbola. The hyperbola, look at the differences between the definition of the two. The hyperbola is the locus of a moving point whose difference. So instead of sum, this time we have a difference. Difference of distances to two fixed points, the foci, equals to a fixed value, which is 2a. It's exactly the same definition, except that this is the sum and this is a difference. Now in the book, these are two different lessons, but I prefer always to teach them as one lesson because these two shapes have a lot of similarities, and we can use these similarities to get used to them pretty quickly. Okay, so let's show you a hyperbola. So this is a hyperbola, okay? So you see this now, these two lines in blue is the hyperbola. Let's show you the calculation. Now look at this. If I have a point here and I'm starting to move this point, let's hide the asymptotes. I'm moving this point here, okay? So while I'm moving it on the hyperbola, I will have two values. There is 9.93 and 3.96. If I take the modulus value of their subtraction, so the difference, I will see that the difference is 6. And if I keep moving it, wherever I move it, yes, I'm going to have different distances, but their difference is always going to be 6. The same thing even if we move the point to the other side, to the other curve here, to the side on the left hand. So if we move it here, we will also get the same difference, which is 6. So this is how a hyperbola is defined. It's defined by the subtraction, by the difference, while the ellipse is defined by the sum. So in the hyperbola, it's the locus of a moving point whose difference of distances to two fixed points or the foci equals to a fixed value or 2a. Okay, now these are the definitions of these two shapes. Let's move on to the standard positions. And now look at this, guys. In the parabola, we had 4 standard positions, and then we had non-standard positions as well. In the ellipse, we have only 2 standard positions. In the hyperbola, we only have 2 standard positions, and you're not going to be required to study the non-standard positions. So you will only study the standard positions only. So let's look at this. This is an ellipse, and we say that this ellipse is in the first standard position. To differentiate between this ellipse and the second ellipse, let's see first of all, why do we call this in the first standard position? We don't have only one focus, we have 2 foci. So these are the 2 foci. Where are they located? They are located on the x-axis. So they are 4 and 0 minus 4 and 0. We don't have one vertex, we have 2 vertices. This is one vertex and this is the other vertex. These are called vertices. And where are they located? They are located also on the x-axis. So the foci and the vertices are located on the x-axis. We don't have one directrix, we have 2 directries. We have one directrix here and the other directrix here, and they cut the x-axis. Okay? And they cut the x-axis. So I hope this is so far is good. So this is the case with what? This is the case with the ellipse in the standard position number 1. If we're talking about the standard position number 2, let's see this one now. So this is now an ellipse in the standard position number 2. You see it's upside down, it's kind of vertical. This ellipse was horizontal, but this ellipse now is vertical, right? So this ellipse is vertical more than horizontal. Sorry. Okay, so this is an ellipse in the second standard position. You notice that the foci are on the y-axis. The vertices also are on the y-axis. The directories, they cut the y-axis. Okay? Now, there is something important about ellipses that you need to understand. We call this, let's bring this a little bit closer. Okay, we call this here the distance from here to here, from 50 to minus 50. This distance here, all of it, we call this the major axis of the ellipse. major axis. We call this distance from here to here the minor axis of the ellipse. And we call this distance from here to here, from the focus to the focus, we call this distance from the focus to the focus the focal length. Again, we call the distance from the vertex to the vertex the major axis. We call the distance from this point to this point the minor axis. And we call the distance from the focus to the focus the focal length. Notice that the distance from this vertex to this vertex is actually 10. It is 5 squares here and 5 squares here. So this is 10, right? And the sum here in the relation is 10. This is not a coincidence. Actually, we said in the definition that the fixed value is 2a, right? We said in the definition that the fixed value is 2a. What is a exactly? A is the value of the vertex, the value at the vertex, So how much is the value of at the vertex? If the value at the vertex is 5, then 2a is 10. So the relation is 10. Okay? So the length of the major axis is 10. This is how long this line is. This line is 10 units. And it is the same as the one that we get from the relation. The length of the minor axis is 8 because it is 4 here and 4 here. Actually, this point, this number is called A, this number is called B. The 4 is called B. And the focal length is equal to 6. It is 2 times 3. This 3 is called C, the same as the C in the focus of the parabola. So we have 3 letters here. We have A and B and C. They're all important. And if we find these 3 letters, this is what we mean by the data of the ellipse. If you find A and B and C, then you found everything that is regarding an ellipse. And we will see how A and B and C are pretty important in solving these questions. Now, the same thing with an ellipse from the second standard position. This is 0 and 5. If I show you the relation is 10 here. Why is it 10? Of course, if I add them, I'm going to get 10. Why is it 10? Because this is 0 and 5. So A is 5. A is always at the vertex. Again, A is the value at the vertex. So the value at the vertex is 5. 2 times 5 is 10. That's why the sum is 10. The major axis, the length of the major axis this time is here on the y-axis. And the length of it is 10. The length of the minor axis is 8. The focal length is 6. Again, this is A, 5. This is B, 4. And this is C, 3. Now, if I move the focus, everything moves accordingly. Now, look at this. If I move it here, and let's zoom out a little bit. If I move it here, how much is A now? 10. So how much is the number in the relation? Is 20, 2a. The relation is always 2a. So this is 10, this is 6 this time, this is 8. So the minor axis is going to be 16, the major axis is going to be 20, and the focal length is going to be 12. We will see this more with the slides now, in the slides. So let's go to the slides. So as we said now, we have 2 standard positions with the ellipse. Now this table might seem intimidating at the beginning, but this table is a very important one. You will find this table on page 225 in your books. I encourage you to open that page and follow this lecture while that page is open, because that page is going to be important for basically all of the exercises that we're going to do. So I'll give you some time, a moment now, just to go and look at the page. You can pause the video, take the book please, and open that page for me. Okay, I hope that you have the page now ready in front of you. Now, the part that we have explained so far is this. So we've talked about the vertices. We said in the standard position number 1, the vertices are plus or minus a and 0. So we've seen, for example, plus and minus 5 and 0, 2 points. The foci are plus or minus c and 0. We've seen this which is, for example, 3 and 0, right? In the example that I have just shown you, they were plus and minus 3 and 0. That's the foci. Okay, if it was SP2, then the point were located on the y-axis. So you'll have a y value, but you will not have an x value. So it was 0 plus minus 5, and here 0 plus minus 3, right? The major axis is 2a. The major axis is 2a. So a is 5. A is 5, so 2 times 5, which was 10, right? And the minor axis was 2b. How much is b? b is 4. How do we calculate b? There is this line now which is important, which tells us the relationship between a, b, and c. Now a is the vertex, right? Is the vertex. C is the focus, the value at the focus, and B is the point which is on the other axis. So how do we calculate B from A and C? We use what we call the Pythagorean relation, Pythagoras theorem. So it's exactly Pythagoras theorem. How do we use Pythagoras theorem? We say it's A squared is equal to B squared plus C squared. It's easy to remember this one if you remember the sketch. Now A, remember that always A is the furthest from the origin. It is far from the origin. C is closer, right? And B is also kind of close. B here. So the largest number is A, right? If the largest number is A, then it goes before the equal sign. And after the equal sign, you put the other two numbers, B and C, because they are smaller. So the Pythagorean relation is going to be A squared equals B squared plus C squared. And this is how we find B. And if you find B from this line, you multiply it by 2, you get 2B, which was 8, I think, in our example. So this is the minor axis. The directories, we've seen the directories in the drawing. The directories were this one and this one. These are the directories. How do you find their equations? First of all, they cut the x-axis. They cut the x-axis at 2 points, this point and this point. And to find their equation, it's always x equals plus minus a squared over c. A squared is from A, from the vertex, and c is from the focus. So again, I'm telling you guys, if you find A and B and C, you can find all of this data easily. The directories in the second 10 position are not cutting the x-axis, they're cutting the y-axis. This is why they are y equals. You see, the directories here, they cut the y-axis, this one and this one. They cut the y-axis, and that's why the equation is y equals, but it's exactly the same relation, plus minus a squared over c. Okay. Now, if we look at a hyperbola, let's look at the hyperbola now. This is a hyperbola, again. Where are these values, A and B and C? Look, A is here, it's the vertex. Look, these 2 points are the vertices. These are A. How much is the value of A? It is 3. And according to the definition, the number that we have here should be 2A, which is 2 times 3, which is 6. Right? So this is, or these are the vertices. So the vertices are A, this one and this one. B are on this other axis, and C are right here. This is the focus, and it's enclosing the focus. Okay, look at this, guys. First of all, we call this axis from A1 to A2. We call this axis the transverse axis. We don't call it major axis or minor axis. We call it the transverse axis. We call this axis the conjugate axis. So it's exactly the same thing. The transverse axis is like the major axis, it's 2A. The conjugate axis is like the minor axis, which is 2B. And this is the focal length. From C1 to C2, we call it the focal length, which is 2C. So it's kind of the same thing. And we will notice that even if we have a second standard position, even if we have a hyperbola like this is a hyperbola in the second standard position. So there are 2 standard positions as well. Either one that is horizontal like this one, or vertical like this one. So if we have a parabola like this, we'll notice that the focus is on the y-axis. It is the furthest from the origin. And then we have the vertex, it's also on the y-axis, it's closer to the origin. And we have B here, which is going to be on the other axis. We have the same relationship. Let me get A as A is 6, for example. So if I show you the calculation, it will be 12 because it's 2 times 6, which is 12. So the vertices are always smaller than the focus. This is called the transverse axis, which is 2A. This is called the conjugate axis, which is 2B. And this is called the focal length, which is 2C. The word major and minor are not used here because simply it's not always that this one is going to be bigger than this one. In the ellipse, the 2A was bigger than 2B for sure. In the ellipse, let me show you the ellipse. In the ellipse, 2A from A1 to A2, the distance, is more than 2B for sure because the ellipse looks like this. It is narrower from here, it's wider from there. So 2A is major because it's bigger. 2B is minor because it's smaller. But with the hyperbola, if you notice carefully, this one is 12, but this one is 16. So we cannot say that this is the major axis, 2A is the major axis and 2B is the minor axis. Instead, we call them other names. We say that this is the transverse axis. The word transverse means cutting, so it cuts the hyperbola because this one cuts the hyperbola. And this is called the conjugate axis because it does not cut the hyperbola. Okay, now if we go back here and we will notice that the vertices are exactly the same thing. So if it is standard position number 1, it's plus minus a comma 0. If it is standard position number 2, it is 0 plus minus a. The foci are the same thing. It's plus minus c comma 0 or 0 plus minus c. The transverse axis is 2a. The conjugate axis is 2b. The directories are also the same. They're a squared over c plus minus, and it's equal to x here, and it's equal to y to in the second standard position. Now, I haven't shown you the directories. The directories are these two lines. So these are called the directories. And also here, the directories are these two lines. Okay, and how do we find them? Same thing, a squared over c for both of them. So you will notice that actually these are the same for the same standard position. These columns, the vertices, the foci, the length of the major axis, the minor axis, and the directories, all of these are going to be the same as long as it is the same standard position. So if it is 1, it's the same thing. If it is 2, it's the same thing. This is again why I like to teach these two lessons together, because they have a lot of similarities. And it's important to notice their differences so that when you solve a question with an ellipse and with a hyperbola, you know what is similar and you know what is different. So the vertices are not going to be different. They're going to be the same. The foci are the same. The length of the transverse axis and the conjugate axis and the directories, all of these things are the same. So what is different? What's different is the following. First of all, the Pythagorean relation. In the ellipse, A is the biggest one. So A is bigger than B and A is bigger than C in the ellipse. And that's why the Pythagorean relation starts with A. Because A is the vertex and the vertex is the furthest from the origin. In the hyperbola, C is the biggest one. C is the furthest from the origin. So C is bigger than A, and C also is bigger than B. Okay, so that's why we start with C. Okay, so in the Pythagorean relation, these two are going to be different. If it is an ellipse, it's a squared equals b squared plus c squared. If it's a hyperbola, it's c squared equals a squared plus b squared. So this is the first difference. The second difference is in the equation, but this difference is quite, it's not that huge. Look at this. If it's an ellipse in the first standard position, the equation should look like this. X squared over a squared, again a, we find a from the vertex, plus y squared over b squared, b is found from the Pythagorean relation, is equal to 1. And you should always notice that a squared is bigger than b squared. So a is bigger than b. And if it is in the second standard position, then you will have it opposite. You will have the y squared over a squared and the x squared over b squared. So the y squared over the bigger number, this is the bigger number, and the x squared over the smaller number. So here, the x squared is on the bigger number, you know it is sp1. If the y squared on the bigger number, it's sp2. In the hyperbola, actually, we don't know which one is bigger. So a squared is bigger, b squared is bigger, we don't know. Sometimes b squared is bigger, sometimes a squared is bigger. So how do we differentiate between the first standard position and the second standard position? It's quite easy. You look at the minus. So this minus is for the y-axis. So the one which is positive is where the vertex is. So if the x is positive, it is standard position 1. If the y is positive, it's standard position 2. You see here the y is positive and the x is negative. That's why it is sp2. This is x is positive and y is negative, so this is why it is sp1. Now, look at this, guys. Regarding the standard positions of 1 and 2, you will notice that the equation is exactly the same, whether it's an ellipse or a hyperbola. The only difference is that with the ellipse you have a plus, with the hyperbola you have a minus. Same thing here, with the ellipse you have a plus, with the hyperbola you have a minus. So this is the first difference between the second difference between them. So the first difference is that we have different Pythagorean relation. The second difference is that we have different signs in the equation of the ellipse and the hyperbola itself. The last difference is the asymptotes. You will notice that with the hyperbola you will have asymptotes, and the equation of the asymptote is going to be b over ax here and a over bx there. Y equals b over ax and a over bx. In the ellipse there are no asymptotes. Let me show you the asymptotes now in the graph. Now these are the asymptotes. These are the asymptotes. To find their equation, we will divide the number on the y-axis by the number on the x-axis, which is b over a. So b over ax, b over a, and then y equals b over ax. If it's from the second standard position, then we will divide the number on the y-axis over the number on the x-axis. It will be a over bx. So here it is b over a, and here it is a over b. So it's the gradient, and the gradient is y over x. So you will divide the number on the y-axis by the number on the x-axis. And we're not talking about the focus, we're talking about the vertices a and b, okay? So the last thing that I need to draw your attention here to a rule here at the end, which is going to be the same for everything. E is called c over a. What is this E? E is what we call the eccentricity. The eccentricity. And we're going to explain more about the eccentricity in the slide after the coming. So we will just delay this point a little bit. This table is very important for all of our calculations, so please find this table in your book, memorize it well, because it's going to you're going to rely on it entirely in solving all of the questions of ellipses and hyperbole. So let's do a quick revision of the standard positions. So we have 4 standard positions, 2 for the ellipse and 2 for the hyperbola. For the ellipse, the standard position 1 is x squared over a squared plus y squared over b squared is equal to 1. Remember that a squared is bigger than b squared. It's the bigger number. And this is how it looks like. So the focus is on the x-axis. The vertices are also on the x-axis. And this is the minor axis, and this is the major axis. And this looks like an alien now. Okay, the second one, y squared over a squared plus x squared over b squared. Remember that a squared is bigger than b squared. So if y is on the bigger number, it means that it's sp2. And this is how sp2 looks like. Notice that the vertices are on the y-axis, and also the foci are going to be on the y-axis, the foci and the vertices. For hyperbole, the first hyperbola here, this is a hyperbola in this first standard position. Notice this is the focus, it's the furthest from the origin. These are the vertices A, and this is the vertex B. A is not more than B. And here, the vertices are on the y-axis, and also the focus are on the y-axis. Okay, can A here, A is not necessarily bigger than B. So A can be more than B. no problem. A can be less than B, no problem. A can be equal to B. They're all good. It's all possible. Here, it is conditioned that A is more than B. But what happens if A is equal to B? If A is equal to B, if these two are equal to each other, the shape here turns into a circle. So this is a circle. The circle is a special case of the ellipse, in which A and B are equal. So the major axis and the minor axis are equal. If they are equal, then we have a circle, a complete circle, okay? So this is why I'm telling you that the circle is a special case of the ellipse. This is the only thing that you need to know about circles this year, that they are a special case of ellipses, and it happens when A and B are equal, or A squared and B squared are equal. Okay, let's talk about the eccentricity. So the eccentricity is E, which is C over A, and we've seen that it's the same for all of the conic sections. So what is the eccentricity exactly? Okay, the eccentricity is a measure of what shape do we have. Look, if the eccentricity is 0, if C over A is 0, then you should know that the shape that you have is a circle. So whenever the eccentricity is 0, the shape that you have is going to be a circle. Now, if you move this a little bit, if it increases from 0, it is 0.12. It is more than 0 and less than 1. So if the eccentricity is more than 0 and less than 1, then what you have is an ellipse. You see, this is an ellipse now. This is an ellipse with two foci. This is the center of the ellipse, and these are the two directories. So it will keep being an ellipse for all the values of the eccentricity. See, it's still an ellipse until we reach to 1. So what happens if you reach to 1? So this is now, look, this is now 98. It's still an ellipse. Now 99, it's still an ellipse. But what happens when we get to 1 is that we lose the ellipse. We don't have an ellipse anymore. What do we have instead? We have a parabola. So if the eccentricity is 1, it makes a parabola. Now, if the eccentricity is more than 1, what happens now is that we start seeing the second shape, the second part of the ellipse coming back from here, which makes a hyperbola. So now we have a hyperbola, and the more you increase it, the closer the hyperbola becomes. So any value now that is more than 1 is going to make a hyperbola, okay? So all of these now are hyperbolae. So this is a hyperbola, just the way we've seen it. So eccentricity has 4 possible answers, or 4 possible values. It can be a 0. If it's equal to a 0, then you have a circle. If it's between 0 and 1, you have an ellipse. If it's equal to 1, it's a parabola. If it's more than 1, it's a hyperbola. This table is very important because they always ask about these values of the eccentricity in the ministry. These are always questions, and they're multiple choice questions or true or false questions. So I can ask you, if the eccentricity of the conic is equal to 1, then the conic is a parabola, an ellipse, a circle, or a hyperbola. I hope this is clear so far. So now I'm going to start with some exercises regarding this lesson. So we will see some exercises regarding ellipses and some exercises regarding hyperbole. Okay, so the first exercise says the following. Find the equation of the conic that satisfies the following conditions. Now, before I start with the question itself, I just want you to draw your attention to this word. In the ministry, a lot of times, they don't tell you whether the shape that you're dealing with is an ellipse or a hyperbola, because they're so much similar to each other. They will just ask you to find out what shape you're dealing with. So they will just say the word conic in their question. They will not say if it's a hyperbola or an ellipse. We will see now how do we recognize if it's a hyperbola or an ellipse. So they say that this conic has vertices of 0 plus minus 4 and the foci of 0 plus minus 6. And what do they want? They want the equation of the conic. Before I'm going to start, I will need to draw first. So I need to draw what's given to me. So what is given is the following. I am given the vertices and the foci. I can draw the y-axis here and the x-axis. Okay, so the vertices are 0 and plus minus 4. Remember that this number now is A. The foci are 0 plus minus 6. Remember that this number now is C. So A is equal to 4 and C is equal to 6. Maybe now you can figure out, now we are dealing with actually, we are dealing with a hyperbola. We're not dealing with an ellipse. Why? Because the focus is bigger than A. C is the biggest number. So this is now is 0, 6, right? And we have also 0, minus 6. We have the vertex as 0, 4, another vertex at 0, minus 4. And because this is the focus, our conic should enclose the focus, so it should look like this. And also here it should enclose the focus. So this is a hyperbola. So what conic is this? This is a hyperbola. And which standard position it is? It is the standard position number 2. Okay? So if it's a hyperbola from the second standard position, so we're starting with y. So it is y squared over a squared minus x squared over b squared is equal to 1. This is the equation of the hyperbola, the required equation. But we know A is 4, so a squared is 16, but we don't know b. So how are we going to find b? We'll use the Pythagorean relation. So which number is the biggest? Is it c or a or b? Of course it is c. It is the furthest from the center, so it's going to be c squared. So c squared equals a squared plus b squared, because c is the biggest number. Now let's substitute. C is 6, so 6 squared is 36, equals a is 4, so 4 squared is 16, plus b squared. Let's transpose the 16 to this side, so 36 minus 16 equals b squared, so b squared is equal to 20. We need b squared actually here, so therefore the equation of the hyperbola will be what? It will be y squared over a squared, which is 16, minus x squared over b squared, which is 20, equals to 1. So this is going to be the equation of the required conic, which is a hyperbola in the second standard position. I hope this question is clear. Let's do another question. So the question says, find the equation of the conic that satisfies the following. The vertices are plus minus 6 and the eccentricity is 4 over 3. Okay, because the eccentricity is more than 1, this is 4 over 3, more than 1. So because it's more than 1, therefore we have a hyperbola. It's a hyperbola, because if it's an ellipse, it's going to be less than 1. So what we have is a hyperbola. And in this question, we know the vertices. We know that the vertices are here, 6, 0, and also here, which is minus 6, 0. These are the vertices. And because it's a hyperbola, so it's going to look like this, enclosing the focus, which is going to be further from the vertex. So this is a hyperbola from the first standard position. So standard position 1. So what is the equation of the standard position 1? This number here, guys, is the vertices, so this is C. So C is equal to 6. Okay, we know that it's a hyperbola, so this is a hyperbola, and we know also that it is from the standard position number 1. So the equation would be like this: x squared over a squared minus y squared over b squared equals 1. Now we don't have a squared, we don't have b squared. The only thing we have is c, and we have the eccentricity. How can we use the eccentricity to find the value of a and b? Let me show you how. E, the eccentricity, is equal to c over a. This is the rule of the eccentricity. Now, what do we know of these? We know the eccentricity itself. How much is it? It is 4 over 3. So we can substitute here 4 over 3 equals, we know how much is C. C is 6. So this is 6 over A. We don't know how much is A. So now we need to find how much is A. How do we do that? I am going to cross multiply. So 4A is equal to 3 times 6 is 18. I will divide by 4 both sides. So A is equal to 18 over 4. After cancelling, it's going to be 9 over 2. So now I've found A. Good. We have found now A. What do we still need to find? We have C, we have A, but we need to find B. How do we find it? Because it's a hyperbola, we're going to use the Pythagorean relation. C is the biggest number. So C squared equals A squared plus B squared. Okay, C is 6. So let's substitute it. 6 squared is 36. Equals A squared, we'll square this number. So it is 81 over 4 plus B squared. Now we should move 81 over 4 to the other side. So we get 36 minus 81 over 4 equals B squared. Okay, let's try to solve this now. We have different denominators. We'll make this over 1 times 4 times 4. So B squared equals to, the denominator is 4. 36 times 4 is 144 minus 81. So we have, so this is going to be 144 minus 81. That is 63. So this is 63 over 4. So that's B squared. So when we come back to this equation now, so therefore, the equation is x squared over A squared. This is A, guys. We square it, we get 81 over 4. But since this is keep and this is change and flip, we will flip this fraction. So I'm going to write the 4 here. It is 81 over 4. I'm going to take the 4 to the numerator. You've seen this in physics, I guess. Minus y squared over 63 over 4. I'm not going to write over 4 here. I'm going to flip it. It's keep, change, flip equals to 1. So this is the equation or the required equation of the hyperbola. So this is the conic that they were looking for. I hope that this one is also clear. I know that at the beginning they might seem a little bit hard, but with just practice, getting familiar with the rules, you will know that it's pretty easy. It's just memorizing the rules and drawing. You have to sketch before solving any question because this is eventually geometry and you need to sketch in geometry. Okay, let's do a third one. So find the equation of the conic that satisfies the following conditions. The vertices are plus minus 5 and the foci are plus minus 4. Okay, let's draw this. Okay guys, look at this. The vertices are always A, the foci are always C. So we have plus minus 4, this is 0, 4, and this is 0, minus 4. This is the focus. These are the focus. The vertices are here, 0 and 5, 0 and minus 5. We notice that A is bigger than C, A is the biggest. We should enclose the focus, so we're going to enclose the focus from the vertex. And also here, I'm sorry, we should enclose the focus from the vertex. So what are we going to have? We're going to have an ellipse. So this is an ellipse. Now this ellipse is in the standard position number 2. Okay, so if it is in the standard position number 2, we know that the equation starts with y. So it is y squared over a squared plus x squared over b squared equals to 1. Notice that we start with y and then x. Okay, now look at this, guys. We have A, we have C, we don't have B. We're going to use the Pythagoras relation. The Pythagoras relation now is going to start with the biggest number. We cannot start with C because C is not the biggest number. The biggest number is A. So we say a squared equals b squared plus c squared. So a squared in our case is 25 because a is 5, equals b squared we just don't know, plus c squared, c is 4, so c squared is 60. I will transpose this here. So 25 minus 16 is equal to b squared. So this is equal to 9. So b squared is equal to 9. So I'm going to use a squared and b squared to write the equation. So therefore, the equation of ellipse is y squared over 25, because a is 5, a squared is 25, plus x squared over 9, because b squared is 9, equals to 1. So this is the equation of the ellipse. Okay? I hope that this one is clear. I think this one, I have this one drawn, I think, here. Yes, it's this one. If the focus is at 4 and the vertex, just making sure, the vertex is at 5. No, it's not the same thing, unfortunately, but it's kind of the same thing. So something like this, maybe the vertex is at 5, but the focus here is at 3. Okay, anyways, let's carry on with some more examples. This is now a new type of questions. It says find the coordinates of the foci and the equations of the directories and the equations of the asymptotes, if there is any, and the eccentricity of the following conics. So look at this, guys. Here we have lots of things to find. They want us to find the coordinates of the foci, so it's C. They want us to find the equations of the directories. The directories are a squared over C. It's going to be either x or y plus minus a squared over c. You can check from the table. The equations of the asymptotes can be either a over bx or b over ax. It depends on which SP it is. This is SP1 and this is SP2 for the hyperbola only. And the eccentricity is c over a, right? So if you just pay attention to everything that we have here, to find them, we just need to find a and b and c. So again, to solve these questions, you always have to find a and b and c. If you find a and b and c, then the rest is just substitution. You substitute in the right place. So let's see. So what are they going to give us to find these things? They are going to give us here the equation. So the equation is x squared over 100 plus y squared over 36 is equal to 1. So what is this equation for? Is this equation for an ellipse or for a hyperbola? For sure, we can see directly that this is an ellipse. Why is it an ellipse? Because we have addition. If it's minus, it's a hyperbola. So this is an ellipse. Is it SP1 or SP2? We can see for sure that this is SP1. Why? Not because it starts with x, no. Because x squared is over the bigger number. Notice that this is plus. They can trick you. They can put y squared over 36 at the beginning and x squared over 100 at the end. So the reason is not because it starts with x. The reason is because x squared over the bigger number. The bigger number is a, so this is a squared here. And this here is b squared. So because a squared is the denominator of x, this is SP1. If a squared is the denominator of y, it's going to be SP2. So this here is SP1. Okay, so it's an ellipse with SP1. This is what we know so far. So we know how much is a squared. How much is a squared? This is x squared over a squared. So it is x squared over a squared plus y squared over b squared equals to 1. So a squared is this number, which is 100. And b squared is 36. What do we still need to find? We still need to find c, right? How do we find c? From the Pythagorean relation. And because it's an ellipse, so a is the biggest one. So a squared equals b squared plus c squared. Let's move b squared here and substitute. So we get 100 minus 36 equals c squared This is 64. So c squared is equal to 64. Okay, so what do they want? They want the focus. So the foci are going to be plus minus c comma 0. You can check that from the table, or you just imagine it. It's SP1. So the focus must be on the x-axis. Since the ellipse is SP1, so the focus should be here on the x-axis. So it is plus minus c comma 0. C squared is 64, so c is the square root of that. So the foci are going to be plus minus the root of 64, which is 8 comma 0. So that's the first thing, the foci. What else do they want? They want the directories. Okay, so the directories are going to be here and here. They're going to cut the x-axis. So there will be x equals, this is the directories. They're going to be x equals plus minus a squared over c. So x equals plus minus a squared is given to me, it's 100. And c is a number that we have found, it is 8. So it is 100 over 8. After cancelling by 8, you can notice that x is equal, you cannot cancel by 8, you can cancel by 4. If you cancel by 4, you get here 25 and here 2. So this is the equation of the directories. Okay, so this is the focus, the directories. The equation of the asymptotes, there are no asymptotes. So there are no asymptotes, and the reason because this is an ellipse. So for asymptotes, there is no answer. Okay, what else? They want the eccentricity. So the eccentricity is equal to c over a. How much is c? C is 8. We found it before. How much is a? A is 10. It's the square root of 100. A squared is 100, so a is 10. And the eccentricity is 8 over 10, which is going to be, after cancelling by 2, 4 over 5. 4 over 5 is less than 1, which emphasizes that this is an ellipse. Okay, because the eccentricity is less than 1. Of course, they will not ask you for all of these in questions since they are multiple choices. They used to do this in direct questions before in the ministry, but now they will just ask you for one thing in the multiple choices. But anyways, this is how we find everything that you want. A, B, C is the most important thing. Let's do another one. Okay, so this one is a little bit different. 9x squared minus 25y squared is equal to 225. We have an important problem here, which is this side is not 1. In all of the equations, in all of the standard positions, if we come back to this table, in all of these standard positions, notice that this side must be 1. But in that question, that side is not 1. So what to do with this? What to do if that side is not 1? What we are going to do actually now is I am going to make it 1 by dividing by 225. So if I divide this side, of course, this term, I will divide all the terms by 225. I can cancel this with this now, I will get 1. Equals. Actually, 9 and 225 can be cancelled by each other. 225 is equal to 25 times 9. So when we cancel, usually these two numbers, if you're asking yourself how would I know in the exam, usually these two numbers, if you multiply them, you get this number. Usually, Usually. So when you cancel 9 with 225, you'll get 25. And when you cancel 25 with 225, you'll get 9. It's not always, but it's usual. So it's something that it's worth checking for. If not, then you have to do it yourself. You have to figure it out. So this is, but usually it's like this. So it's x squared over 25 minus y squared over 9 is equal to 1. Okay, so what is this now? It's a hyperbola. It's a hyperbola. Is it SP1 or SP2? You don't look at the bigger number to decide. No. You look at the sign. Which one is positive and which one is negative? Because x is positive, it is going to be SP1. If x is negative, it's SP2. Okay, this number now is a squared. So a squared is equal to 25. Not because it's the bigger, no, because it is the positive one. And b squared is equal to 9. B is going to be always the negative one, and a is going to be always the positive one. So this is a squared, this is b squared. How do we find c squared? Now, because this is a hyperbola, the Pythagorean relation starts with c squared. It's the biggest number. So c squared equals a squared plus b squared, which is 25 plus 9, which is going to be 34. So c squared equals 34. Okay. Now what do they want? They want the focus. So let's start here. So the foci. Because this is SP1, the foci are plus minus c, comma 0. C is the root of this number. Because it has no root, I'll just keep it inside the root. So it's the root of 34, comma 0. I cannot simplify it, so I'll just leave it like that. The directories. Now this is SP1. So the directories must cut the x-axis. So they are x equals plus minus a squared over c. So x equals plus minus a squared is 25 and c is the root of 34. Okay, so this is the directories. Now the asymptotes. Do we have asymptotes here? Yes, we do. So the asymptotes. On the y-axis, you will have b. On the x-axis, you will have a. So the asymptotes are going to be y equals plus minus the y over the x. b over a and then x. How much is b? b is 3. b is 3. It's the root. And how much is a? a is 5. So it will be y equals plus minus 3b over 5, which is ax. So this is the asymptotes. I'm sorry if this is not organized well. The last thing is the eccentricity. So the eccentricity E is equal to c over a. C is the root of 34 and a is 5. Now the root of 34 is more than 5 because it is more than 25. The root of 25 is 5. The root of 34 is close to 6. It's between 5 and 6, is close to 6. So this is 6 over 5, which is more than 1. And if it is more than 1, it just emphasizes that this is a hyperbola we're dealing with. I hope that this question is also clear. Let's move on to one more question. This is a question that came last year in the exam. Find the coordinates of the foci, the equation of the directories, the equation of the asymptotes, if any, and the eccentricity of y squared equals 4 times 8 minus x squared. This was a question that was last year in the exam, and let's see how do we solve it. So first of all, I'll open the brackets. So y squared equals 32 minus 4x squared. The second thing I will transpose this one because it's negative. So y squared plus 4x squared equals 32. The third step I will do is I will divide by 32 because I want this side to be 1. So divide by 32. So I'll cancel 4 with 32. So I will get y squared over 32 plus x squared over 8 equals to 1. Okay, so is this an ellipse or a hyperbola? It's an ellipse because we have a plus, not a minus. So it's an ellipse. Okay, which one is a squared? This one or this one? This one is a squared because a squared is the bigger. What do we have on top of it? We have y. So this is SP2, not SP1. And the ellipse in the SP2 looks like this: y squared over a squared plus x squared over b squared is equal to 1. So how much is a squared? By comparing the two equations, a squared is 32 and b squared is 8. Now how do we find c squared? We will use Pythagoras. Okay guys, in this question, the Pythagorean relation starts with a because it's an ellipse. So a is the biggest one. So a squared equals b squared plus c squared. A squared is 32 equals 8 plus c squared. Move the 8 to the side, so 32 minus 8 is equal to c squared, and this is going to be 24. So c squared equals 24. Okay, now the focus. Now we can find what they want. The focus, because this is SP2, so it is 0 plus minus C. It's going to be in the Y. So 0 and plus minus the root of 24. The root of 24 can be simplified. This is 4 times 6, so it is 2 root 6. So we can say that the focus is equal to 0 plus minus 2 root 6. That's the focus. The directories, because this is SP2, guys, look, this is SP2, it looks like this, it's vertical, then the directories are here and here. They're cutting the y-axis. So the directories are going to be y equals plus minus a squared over c. So we have here y equals plus minus a squared is 32. So we have 32 here, and c is 2 root 6. So we can cancel 32 with 2, we get plus minus 16 over root 6. This is the equation of the directories. The asymptotes, we don't have asymptotes. The eccentricity is going to be c over a. C is 2 root 6, and a is the root of 32, the square root of 32. Okay, so I can simplify this further. The root of 32, 32 is 16 times 2, so it is 4 root 2. I can cancel the 2 with the 4. I will get root 6 over 2 root 2. Okay, and I trust that this is going to be less than 1 because it's an ellipse. All right, I hope that these are all clear so far. Notice that the table is important. Knowing the table well is important. Also the drawings. If you know the drawing of each one of them, it's not going to be that hard. We still have 2 more examples to go. Let's do this one. This one says, find the equation of the hyperbola. So in this question, they have specified it's a hyperbola. They want the equation whose foci are plus minus 8, 0, and one of its directories is x is equal to 4. Okay, let me show you this one. So the foci is C, so this is C. So here, C is equal to 8, okay? The directory is x equals plus minus a squared over C. They say here one of the directory, and they gave us the positive one. So here they mean that this is 4, which is x is equal to 4, equals the positive, not the negative, only the positive of a squared over C. Okay? Because the directories, again, the directories are x equals plus minus a squared over C. But since they gave us the positive one, then they mean this one only, positive a squared over C. So positive a squared over C is equal to 4, because x is equal to 4 according to the question. Cross multiply here, so a squared equals 4c, and c is 8, so multiply it by 8, so a squared equals 4 times 8, and a squared is equal to 32. Okay guys, look, I am just looking for a and b and c directly, because these are important. I know that if I find them, I'm going to do everything that they ask me for. Of course, c squared here is 64, okay? Because this is a hyperbola, then the Pythagorean relation starts with c. So c squared equals a squared plus b squared. Now I have c squared, it's going to be 64, equals a squared, which is 32, plus b squared, which we don't know. We move this here. So 64 minus 32 equals b squared, and b squared equals 32 as well. Notice that a squared and b squared are equal. It's fine. This is fine with hyperbola, hyperbole. But with ellipses, if this happens, then it's not an ellipse; it's a circle. But with hyperbole, it's fine. So what is the equation? Is this SP1 or SP2? It is SP1. And why is it SP1? Because in the focus, C is in the, you see C here is at the x coordinate of the point. And that's why this equation is SP1, okay? If it's SP1, then The equation, then, okay, look at this. We have a hyperbola, and it is SP1. So the equation is going to be x squared over a squared minus y squared over b squared equals to 1. So let's write them down. So we're going to have the following. So it's x squared, a squared, which is 32. So this is 32 here, minus y squared over b squared, which is also 32, is equal to 1. This is the equation of the hyperbola. Now notice that if these two numbers are equal and this is a plus, it's a circle. It's a special case of the ellipse, which is a circle. But if it's minus, it's a hyperbola. And by the way, this hyperbola, I just wanted to give you some notes here. This hyperbola, if you have a hyperbola in which you have the equation is x squared over a squared minus y squared over a squared is equal to 1, I mean these two are equal, this hyperbola will have an eccentricity of root of 2, always. The eccentricity of this hyperbola is going to be root 2. If these two are equal and they ask you to find the eccentricity, it is always root of 2. And one more thing, the asymptotes of this hyperbola, the asymptotes, if they ask you to find the asymptotes are always y is equal to plus minus x. So these two are always true whenever we have a hyperbola where this one and this one are equal. If a squared equals b squared. So this is if a squared is equal to b squared, this happens. This is just some extra information. Let's do the last question. So the last question says, find the equation of the hyperbola whose foci is plus minus 8, 0, and the asymptotes is y is equal to x. Now notice that here, I know that this asymptote is going to have equal a and b, and actually it's going to be the same as the previous example. So let's see. But how do we find it? Let's see. This is C, sure. So this is a hyperbola. Is it SP1 or SP2? It is SP1. How do we know it's SP1? Because we have value at the x coordinate. So it's a hyperbola SP1. So the equation is like this: x squared over a squared minus y squared over b squared is equal to 1. Okay, let's see what do we have. We have C. So C is equal to 8. C is equal to 8. We have the asymptote. We know that the asymptote, if it's SP1, in SP1, we know that the asymptote is plus minus b over ax. But they gave us only the positive, so they don't want the negative. And x is x, y is y, so this number here, which is 1, is equal to b over a. So b over a is equal to 1. Let's cross multiply. So b is equal to a. Okay, we don't know how much is b, we don't know how much is a. However, we can still use the Pythagoras relation, which is c squared equals a squared plus b squared. We know how much is c. How much is c? C is 8. So 8 squared is 64 equals, let's leave a squared as it is, but let's replace b by a because they're equal. So instead of writing b squared, I'm going to write another a squared here. So it's a squared plus a squared because they're equal. A and b are equal. What do we get from that? A squared plus a squared is 2a squared equals 64. So a squared equals 32. Good? And if a squared is equal to 32, then also b squared is equal to 32. And because they're equal, this is the asymptote. Look, the asymptote is 1x, as we said in the note before. And the eccentricity here is going to be root 2. And the equation, so therefore, the equation of the hyperbola is going to be x squared over 32 minus y squared over 32 is equal to 1. Exactly the same equation as the one that we saw in the previous example. So with this example, we'll be done with everything that we had to learn for this year. We'll be done with chapter 4 and everything that you need to know in chapter 4. For some extra exercises, I encourage you to do these exercises. There's some ministry questions, multiple choices and true, false, and also direct questions. Please work hard. If you face any problem, ask me anytime. You can ask me via WhatsApp, via Facebook. And inshallah, I'm going to try my best to respond as fast as I can. Study hard, study well, and I hope that you will all get great grades at the end of the year. So until then, until I see you again, I wish that you have the best of luck, all of you, and I wish that you stay safe and sound, and peace.